stop talking about producing illegal drugs and start talking about hydrocarbon derivatives. So folks, up until this point, everything we have considered was a hydrocarbon. It had hydrogen and carbon, and that was it. But there are so many types of organic compounds that what we've seen so far just barely scratches the surface. So I've given you just a little selection of what is actually a fairly massive table of different organic compounds that are classified according to something called their functional group. The term functional group would absolutely get used. I've seen it in diploma questions before, and if you look at the practice ones, you'll see it, where we'll give you some crazy molecule that you've never seen and would never be able to name, but you can identify which functional group. In particular, a special arrangement of atoms that is mainly responsible for the chemical behavior. So we are going to talk about the 4 that are listed there, even though in real life there are way more than this. If you take organic chem in university, then you will get to learn about how far this list really goes. We are going to talk about these 4 though. Alcohols, which would be the same type of compound that is found in alcohol that a person would drink. Not many of you, because you're not old enough, unless you're 18, in which case you've tasted alcohol, perhaps, I don't know. But the rest of you have never tasted it, ever. You don't even know what I'm talking about. I know, right? Because you've never heard of it. So there's this stuff called alcohol that's found in beer and wine, and those are grown-up drinks that mommy and daddy might have. Okay? Yep. So the functional group for an alcohol is a hydroxyl group. That is a term that you will see that will get used. And while there could be lots and lots of things attached to it, there could be 10 carbons, 5 carbons, there could be branches, there could be double bonds. The thing that makes it an alcohol is just this section. A carbon attached to some other stuff, but specifically attached to an oxygen and a hydrogen. That's the hydroxyl group. Now here, there's an example and the generic formula, but I'm going to show you the naming rules for alcohols in just a minute. We will also talk about alkyl halides. These are molecules where there is carbon and some halogen. Halogens are things like chlorine, fluorine, bromine, all the things from family 17. We are going to talk about carboxylic acids. They have this functional group, so the carboxyl group. And I like to point this out even though we're not going to get to carboxylic acids today, because I want you to notice how similar these two look. They both have an OH, but one of them also has carbon double bonded to oxygen. Frequently, questions will try to trick you into thinking that you have an alcohol when really you have a carboxylic acid, because you'll see the OH and say, oh yeah, alcohols have the OH group, that's what it is. But if there's an OH and that other oxygen, it's not an alcohol anymore. Then we're going to see this other weird set of compounds that you've likely never talked about before that's called an ester. They have a functional group that kind of looks like a carboxyl group, but instead of having a hydrogen at the end, there's another carbon. So these two kind of look alike, and then carboxylic acids kind of look like alcohols. So they all have something in common with each other. The one that kind of stands out is the alkyl halides. Usually people don't have trouble distinguishing that one from the other 3. But because the rest of these all have oxygen as the 3rd type of atom, sometimes it's easy to mix them up. So you have this little summary table so that once we've gone through lesson 5 and 6, you could come back to this and say, okay, these are the derivatives that we've looked at. So we're going to talk about alcohols first. Alcohol has the hydroxyl functional group, which we just highlighted, but we'll write again. So aside from, say, identifying that something is an alcohol, which I could see, now that you have lots of categories, a typical kind of question could be one that asks you, hey, here are a bunch of molecules, which type are they? Some of them could be alkenes, some of them could be aromatics, some of them could be alcohols. When you name and draw an alcohol and you look at the root, we want the longest chain that includes the hydroxyl group. And you're basically going to name that chain as if it was an alkane. So when we say name the parent alkane, we're going to look for the chain where the hydroxyl group is part of it, and we're going to count how many carbons are in it and name it like it was an alkane. Then we're going to change the suffix. The suffix will always be OL. And when we consider the suffix, kind of like when we considered the suffix for an alkene or an alkyne, we're going to indicate the position of the hydroxyl group. So that means which carbon by a number. So if it was attached to carbon number 2, I would put 2-ol at the end. Now, when we number the parent chain, we will begin at the end of the chain nearest the hydroxyl group. So the question will arise here, okay, what's more important? Is the hydroxyl group more important? Or what if there was a double bond? Would that be more important? There's actually a big, long diagram that illustrates the order of importance. But the way that I'm showing you things kind of goes in the order of importance. And alcohol is more important than the position of the double bond. It would take precedence. So I will endeavor to not ask you on a test to decide between a double bond and another functional group in terms of how to number carbon, and the diploma won't either. Sometimes in the practice questions, I put them in there so that you can see that in real life it can happen, and so that you can practice naming things with more than one functional group. But it's too much to ask you to know just for this level of chemistry. Now, there might be more than one hydroxyl group. That could happen. So if there's more than one hydroxyl group, we would use a prefix, and this would be on the suffix. So that's a mouthful, a prefix on the suffix. What I mean is, let's say there were 2 hydroxyl groups. The end of it would be diol. I would be putting that at the end of the word. Now, in this case, and someone asked me this the other day, can we drop unnecessary vowels? Here is a place where we're dropping vowels. Alkanes end with an E, but we're going to drop the E because our suffix starts with a vowel, an O. We haven't gotten rid of the E at the end before because we haven't needed to, but if I consider when I named the root, I would be naming it like an alkane, like pentane or hexane. There's an E at the end of the word. We're going to drop the E. Now we identify the prefix, and that is alkyl side groups. Now in real life, yes, of course, there could be things that are not just plain old alkyl side groups, but it's the only type that you will be responsible for naming. So methyl, ethyl, propyl, butyl, those types of things. Now those are the rules. Basically, it's the same rules as all of the other things with slight changes to what the suffix is or how we write it. So if we look at the examples, there are some alcohols that we can name. The first few don't have any branches. So if you look at this one, and this one, one of the things that I find happens to people is they get carried away with counting. Now, when it's written as a condensed or a structural diagram and you can see the letters, the C's and the O's and the H's, I don't think that it happens as much. This one has 1 carbon. So I would call it methane, right? I named the parent alkane. Normally I would write an E there, but I know I'm going to get rid of it later on, so I'm dropping it right away. So one carbon is methane. Then I change the suffix to OL. Now it says I have to indicate where the alcohol is attached with a number. But here's a case where you don't need to, because there's only one place I could have attached that hydroxyl on the only carbon that there is. When you see a structure written like this, here's what it looks like in all reality. The O is attached to the carbon, and then the H is on the other side of the O. So when I ask myself what's attached to carbon, 3 of the things that are attached are hydrogen, and then the 4th is the oxygen. Now because no matter where I put the oxygen, it's on the one and only carbon that's there, I can leave the number out. In the second one, this would be ethane if I named the parent alkane, because there are 2 carbons. I would normally write an E, but I know I'm going to drop it, so I leave it out. And this one just gets called ethanol. Again, no number. Now why? There are 2 carbons. Couldn't I have put it on either carbon? Shouldn't that be different? No, it shouldn't, because the rules say you start numbering your carbons closest to the hydroxyl group. So whichever carbon I put the OH group on, that would be carbon number 1, and it would be called ethanol either way. Now, when we get to the third one, we have to start saying where the hydroxyl group is attached. Since there are 3 carbons, I would call this propane. I know I'm going to drop the E, so I'm leaving it off. And this time I am going to give a number indicating where the hydroxyl group is. Now what's different between this one and ethanol? I could have put the hydroxyl group somewhere else. If I had put the hydroxyl group somewhere else, it might look like this one. Now what is that? Well, let's count how many carbons there are in a continuous chain. 1, 2, 3. That is also based on propane. So where is the hydroxyl group this time? Well, it's not on carbon 1. It's attached to carbon 2. So this would be propane 2-ol. And it doesn't look the same. Propane 1-ol and propane 2-ol don't look the same. So I needed those numbers so that I knew where the hydroxyl group was attached. So for the first 2 small alcohols, I didn't need a number because no matter where I put the hydroxyl group, I would have called it the same thing. Now there's a couple more examples. One of them is to show you compounds that have more than one alcohol in them. We'll just pretend that this is a straight line. It was zigzaggy for a reason that I didn't intend, so we'll just pretend it wasn't. If I look at that compound, I have a few things going on. First, there are 1, 2, 3, 4, 5 carbons. When you're looking at a line diagram, try not to get carried away. The end of a line is a carbon unless there's another letter there. So the ends of the lines here and here, those aren't carbons because it clearly shows you that there's an O and an H. So when you're counting, make sure that you're really counting where a carbon is. So I've counted that there are 5 carbons, 1, 2, 3, 4, 5. So I know that pent is my root. But now, is this an alkane? Oh, it's not. It's an alkene. So when I notice that that is happening, instead of calling it pentane, I need to name it as though it were pentene. So I have to decide, where is my carbon numbering going to start? Should I start it here and have it go 1, 2, 3, 4, 5, or should I go the other way? Well, if I do it like that, my hydroxyl groups are on carbons 1 and 2. If I do it the other way, my hydroxyl group would be on carbon 4 and 5. Ooh, bad. Don't want the hydroxyl group to be at the end. So the way I've numbered it is the way we would do that. So instead of naming an alkane as the root, I'm naming an alkene. I need to say where the double bond is. It's between carbon 3 and 4. So pent-3-ene. And just like an alkane, I'm dropping the E at the end. So instead of naming the parent alkane, I named the parent alkene here. Now, for my hydroxyl groups, there are 2 of them. One of them is attached to carbon number 1, the other is attached to carbon number 2. So I would put 1, 2. I always separate numbers with commas, but between numbers and letters, dashes. So 1, 2, diol. Pent-3-ene, 1, 2, diol. Sounds like a fake made-up word, but it's not. It's organic chemistry. Now, do I think all of this would happen on one test question? Unlikely. Not where you have to name it anyways. But this is just showing you that you can put together any of the rules that we have. This last one is an example where you have branches and you have the hydroxyl group. So just remember that the hydroxyl group takes precedence when you're numbering the carbons. And I'd like you to see if you can come up with it. So I'll just walk you through how I would name this one. What I circled has 5 carbons. 1, 2, 3, 4, 5. The ones in the middle are just ends of lines, and the ones in the end were named. There are 5. So I name this like it's an alkane, because that's what it is, single bonds. Pentane, but I don't write the E, because I know I'm going to get rid of it. Then when I ask myself how to number the carbons so I know where to put the hydroxyl group, how should I number them? Left to right, right to left. I heard someone say it doesn't matter, and I agree for the hydroxyl it doesn't matter, but for the other things it does. So we're going to go left to right with the numbering. So 1, then 2, then 3, then 4, then 5. Now, if I look at the hydroxyl, the OH, it's on carbon 3 no matter what. So it doesn't matter which way I go, it's absolutely on carbon number 3. So my suffix is 3-ol. Now when I look at my branches, since it didn't matter which way I went for the hydroxyl group, I'm going to revert back to my other rules. Give the branches the lowest number possible. So even though hydroxyl is more important, since it didn't matter for hydroxyl, I always fall back on the next set of rules that preceded it. If I start at the left, my branches are on carbon number 2 and carbon number 3. So I should be calling this 2, 2, 3 trimethyl pentane 3-ol. 2 and 2 because there are 2 methyl groups, one on the top, one on the bottom, on carbon number 2. And then the third one is on carbon number 3. If I had numbered my carbons the other way, it would be 4, 4, 5, or 4, 5, 5, and that would be bigger numbers, and we wouldn't do that. Does anyone have questions about those? Okay, so just like with our other compounds, you need to know how to draw them as well as how to name them. So if we take a look at how to draw them, you should follow the same pattern that you do when you're naming them. Start with the root. So I'm finding the root. They should all be based on alkanes. So there's my root, butane. 1, 2, 3, 4. I know that on carbon number 2, I'm going to put a hydroxyl group. Now it's pretty typical for the hydroxyl group to get drawn as a condensed diagram where I don't depict the bond between oxygen and hydrogen. And I know that on carbon number 3, there's a methyl. And usually our side groups are just condensed all the time. Now, it didn't matter that I put the hydroxyl on the bottom and the methyl on the top. You could have put them both on the same side or vice versa. But now I can fill in all of the hydrogens that I would need so that I have a structure where every carbon has 4 bonds. Now we could base this on something that's cyclic. So this next one, notice, has cyclopentane as its root. Anytime something is cyclic, wherever the functional group is assumed to be carbon number 1. So in the second one, just like with our double bonds and triple bonds yesterday, wherever the alcohol is attached, we assume that that functional group, which is the more important one than the branch, is carbon number 1. Now, in the third one is an example where we have a phenyl group. Some of you might ask, doesn't phenyl have 6 carbons and hexane has 6 carbons? How come it's not the root? And I think you'll see that in this case, it's because the hexane has the OH groups, which will contribute more to the functionality of it than the benzene group will. And the last one is similar to the first one, where we just have plain old nonane. It's not cyclic, no phenyl or anything like that. So I'd like you to take a few minutes and see if you can sketch a drawing of these. So folks, I have my pictures up here of these structures so that you can check on them. If you look at the second one, I decided to put my OH group on that top right carbon. You didn't have to put yours there, but wherever you did put the OH group, that is carbon number 1. That means that the ethyl side group should be on the next carbon. Okay, so it's also not a rule that you have to count things clockwise, although I think you'll see that's the way we will typically count things on a cyclic structure is clockwise. But all that's important is that on the carbon next to the one with hydroxyl, you have the ethyl side group. Now with ring structures, it's common to use line diagrams for the ring and then condensed for the side groups. For the next one, I just gave you both versions, the condensed structural and the line diagram. The thing that I just want to highlight here, for example, is that there was a carbon that didn't have any hydrogen attached to it. And sometimes people forget that when there's lots of branches going on, it's easy to miscount a hydrogen. The other thing I like to mention is that when you're counting hydrogens, maybe don't forget that there's a hydrogen in the hydroxyl group and that if you were trying to come up with the empirical molecular formula, it would count. Now, if you're going to draw a line diagram for benzene, which is fine, go ahead, but someone tell me how many carbons and hydrogens are in that structure. This part gets tricky. Yeah. So, if it was benzene all by itself, just like this, it's C6H6. There are 6 of each of them. But if you look, I had to attach the benzene to this carbon here. So, I had to take away the hydrogen that was there so that I could make a bond. And I feel like that little detail is the one that gets lost in the shuffle. Now that it's attached, there are 5 hydrogens, 1, 2, 3, 4, 5, and the 6 carbons in the ring. The 6th hydrogen got replaced by that bond we needed to create to attach it. So if you're drawing line diagrams, which you typically would for benzene, you just have to keep that in mind. All by itself, it's C6H6. But once I attach it to something else, the 6th hydrogen had to get replaced so that I could attach it. Same thing would be true down here. Now, does anyone want to ask anything about those drawings? Okay. If we consider alcohols, unlike everything we have talked about so far, they are actually polar. And it's because of the hydroxyl group. Now, not all alcohols will act like a typical polar molecule, but methanol and ethanol are miscible with water. I can mix them with water. That is why one day when you're old enough, you could mix alcohol with something else and have it not separate as a drink, unless you're mixing it with something like milk where it can curdle and it's gross. No, but you don't know anything about this. You've never heard of a paralyzer or anything like that. So If you're thinking about this mysterious rum and Coke that you've heard of but you've never tried, what's in Coke? Bunch of water, sugar also, but the reason it works to mix it is because the alcohol that we're mixing it with is polar. If it weren't, you would get a layer of alcohol and a layer of pop, and they would separate, and it would be weird. Now, please notice that this solubility has its limits. As the hydrocarbon chain becomes longer, now that little hydroxyl group that was on the end isn't contributing as much to the overall property of the molecule. Larger alcohols are less soluble. So, if I think about what's going on, the bigger alcohols get, the less soluble they are, but the bigger molecules get, the higher their boiling points are, so it kind of has the opposite effect. If we compare hydroxyl groups, so alcohols, to some of the other functional groups we've seen, like alkanes, alkenes, alkynes, they have much higher boiling points than if we compare them to alkanes or alkenes or alkynes. So, if I consider my little list, now alcohols are at the top of the list for boiling points, then alkynes, then alkanes, then alkenes. There's also a division now. Alcohols are soluble. I can mix them with water. I cannot mix alkynes, alkanes, alkenes with water. Now, because alcohols have much higher boiling points, it explains why the smaller alcohols, so 12 carbons or less, they're all liquids. If something is a liquid at room temperature, it means it hasn't boiled yet, so that means its boiling point must be higher than whatever room temperature is. Now that's the story on alcohols. The other side of the story today is alkyl halides. So, very similar set of naming rules with some slight changes. All an alkyl halide is something with a group 17 atom. An example of something you might have actually heard of in your daily life is a CFC, chlorofluorocarbons. This is a group of alkyl halides that affects the ozone layer, acts as a greenhouse gas. So they used to be used in aerosol cans. They shouldn't be anymore, but that was where you might have seen them. Now, when we name an alkyl halide, really, we're just naming an alkane, and we're calling the halogen a branch. So we are going to locate the longest chain that includes the halogen atom. Then we name the parent alkane, just like we did for alcohols. Then we identify the prefix, and here the prefix gets some more stuff. Normally the prefix is just our alkyl side groups, but now we get to name halogens and alkyl side groups both as part of the prefix. So we're going to number the parent chain starting at the end nearest the halogen atom. So these are more important than other alkyl branches if we're naming and numbering them. Then we name and number alkyl side groups like we would have before, but also we're going to name and number where the halogens are attached. So we're going to look for the number or the numbers of the carbon atoms bonded to the halogens, and we will use prefixes specific to them. So for example, we might use the prefix fluoro, iodo, chloro, bromo. So it depends on which halogen we're talking about. In a chlorofluorocarbon, obviously we used chloro and fluoro because chlorine and fluorine were our halogens. If there are two or more of the same halogen, we use a prefix on the prefix so that we can say how many there were. And if there's more than one type of halogen, they go alphabetically. So that's why chloro came before fluoro, because C comes before F in the alphabet. Now, does anyone want to ask any questions about the rules before we do the examples? Okay. So if we take a look at some of these, the first one has 2 carbons in the main chain and there's a double bond. So the parent molecule is actually an alkene. So that's ethene. I don't have to call it F1 or F2-ene because there's only one spot I could have put that carbon to carbon double bond. So I don't have to say where it's located. Now if I look at what's attached to that ethene, there are 4 fluorine atoms. Now, normally I would put numbers to say where the fluorines are attached, but is there any other place I could have put all 4 of them? There's not. So this is tetrafluoroethene. Now the next one, what's the root of it? Well, look in the middle. That's benzene, alternating double bonds, so benzene will be my root. With benzene, I don't have to put numbers to say where those not quite double bonds are located. Now when I look at that, I can see a chlorine atom at the top and a chlorine atom at the bottom. Since this is a cyclic structure, I should make one of those be carbon number 1. So if you look, because they're on opposite sides, I could really give either of them carbon number 1. I'm going to say that the first one is carbon number 1 and go like this. You'll see that if I went clockwise or counterclockwise, I would have wound up with the same scenario, where on carbon number 1 and carbon number 4, I have a chlorine atom, so this becomes 1,4-dichlorobenzene. Now the third example shows us what to do if we have more than one type, because in the other two we had just fluorine or just chlorine, and the rule is alphabetical. So if I look, there are 1, 2, 3, 4 carbons in the chain. Now I have to number the carbons, and I should number them closest to the halogens. So those will be my numbers on the parent chain. Now, would anyone like to tell me what the name of this should be? Yeah. 1, bromo. We'll say 2. I think you said 3, but I think you meant 2. Chlorobutane. We named the parent butane, 4 carbons in a chain. Put bromo first, not just because it was on carbon number 1, but because B comes before C in the alphabet. Now, does anyone want to ask anything about any of those examples? Okay. Yeah. Always alphabetical order. Yeah. So we have a few examples here for us to draw. Always start with the root. So heptane is our root. 1, 2, 3, 4, 5, 6, 7 carbons in a chain. On carbon number 2 and carbon number 3, I have a bromine. And then on carbon number 3 and carbon number 4, I have a fluorine. The halogens work like they were just regular alkyl side groups, except instead of being alkyl, they're halogens. So take a moment and try these other two yourself. Now, folks, I'd encourage you to check what you have drawn just to see if it matches mine, or, especially because these are cyclic, if you twisted it or rotated it, does it match mine? I have a habit of making carbon number 1 on the right top piece on cyclopentane, but on benzene I like to make number 1 on the top. It's a cyclic structure, so that's just my drawing habit. What's important is how far the branches are away from each other, so that we could theoretically number the carbon that has those 2 chloro branches number 1 and the one with the fluoro branch number 2. Now in 135 triiodobenzene, I know that you want to not have vowels in a row, but you have to. There needs to be vowels in a row there. And it's just important that there's a branch, a space, a branch, a space, a branch, a space. And you could have very easily have drawn this version for benzene with the alternating double bonds and had the iodines attached the same way. Now,